Good afternoon, everyone. My name is Chen Shengqi. I'm from the Pacman Lab, Tsinghua University. And today, I'm going to introduce our work, HypeReca, distributed heterogeneous in-memory embedding database for training recommender models. This work is jointly done with Jiaao, Huang, and our corresponding author is Zhai Jidong. By the way, the first author, Kezhao, was unable to come here in Boston, and he kindly asked me to take his graduation badge here, so he is now here with me. Okay, so let's get started. So we all know deep learning-based recommendation models, or we call it for short DLRM, is an important workload in the industry. Many companies use it to host billions of users to trillions of content every day. It is mainly used to predict the CTR or click-through rate of a specific content of a specific user. So typically, a DLRM consists of two parts, a sparse part and a dense part. The sparse part consists of embedding tables, typically huge embedding tables, that is used to convert the IDs of entities to pre-trained or not pre-trained embedding vectors, or we call it feature vectors. Then the dense part, it is a typical neural network models that are used to extract the relationships between the items. They are typically consisted of linear layers and not that large compared to like LLMs. So a training sample or input data of DLRM includes multiple items. So the data should be collected from different embedding tables. So the items are naturally unevenly accessed in the embedding tables. For our observation and experiments, in distributed training, the data movement will be the most significant bottleneck of the whole training process. So let's see an example. Here's the visualization of a training iteration. Let's take a look at the forward phase. So the first sparse part takes up a good portion of the time with low GPU utilization because of the communication and data movement. And later, the dense part takes only a small portion of the time, but with really relatively high GPU utilization because of like the jam operation. Okay, so where does all these overhead comes from? So the all-to-all communication overhead comes from a typical setting of hybrid parallelism used in training distributed recommender models. The data are naturally divided into local batches on different workers, and samples in each local batch would require embedding data for almost all other workers because these embedding tables are sharded. The items are originally in the host memory of different workers. Then the dense part, they are replicated on the GPUs, typically a data parallel fashion. So we have to reorganize and copy the data from different host workers to different GPUs. And such reorganization is typically implemented with the all-to-all collective communication, similar to the MOE one, but we copy more data likely. So the all-to-all communication, as we all know, always becomes the bottleneck of applications. So to optimize this, our intuition is to reduce the volume all-to-all. So let's inspect some real-world data sets, and we can find some interesting results or patterns that might give us opportunity to do so. First is Kaggle. It is a widely used data set. First appeared in Kaggle context. So when we sample 100 batches in a Kaggle dataset, we can find that 2.2% of the items appear in more than 25 batches, not showing in only 5 batches. So these frequently see items can cover more than 90% of the access. You can see the cumulative distribution function here, 90% access to the embedding tables. And on the right is the example of a dataset called Taobao. It's released by Taobao, obviously. And a similar trend shows that only 13% of elements can contribute to more than 80% of the access. So by inspecting these two datasets, we can see a chance to reduce the all-to-all communication if we can alter the partitioning method of these frequently visited items. But this is not easy. We all know important The most important thing in training distributed models is to scaling up the distributed training. We have to leverage more devices. So the communication cost would harm the scalability because it's expensive all-to-all communication. But if we want to utilize the pattern to reduce the communication volume, it is also non-trivial. We need to design some delicate and careful fine-grained data management methods before we can alter that pattern. Or otherwise, the data management would become the new bottleneck. So before digging into details, let's first see the overview of our system, HypeReca. It is a replacement of the original hybrid parallel embedding layer in the distributed DLRM training settings. So our system works as a standalone database-like module working independently of any original training engines like PyTorch or TensorFlow or something like that. Yeah, our system has 4 main interfaces, or we call it APIs or components or whatever you like. So it is prefetch, pull, push, and update. So first, it has a function to convert the input IDs to the internal location information using a technique we will discuss later called DIT, or decentralized indexing tables. This process is called prefetch because it can be called and be integrated into the data loader of the training process. So second, we need to move the data actually from CPUs to GPUs, or from host memory to GPU memory. So this is where we call this pull operation. The system HypeReca will load the actual embedding data onto the GPUs during the training process. The system internally manages different embedding vectors in different locations. As you can see here, we have different embedding chunks, and we have a special R chunk. I will explain this later. So we have to maintain the internal data consistency as well as achieve the low communication overhead. So finally, the push and update operations. So by the end of each training iteration, we need to update the gradients calculated by the neural network, by the optimizer, into the our system. So we have these 2 operations. Okay, so what challenges are brought by our fine-grained parallel strategy? So typically, the IDs are mapped to the locations using simple hashing. It's really simple because it should be calculated really fast, so it's a simple hashing. But in our way, we use our own dedicated fine-grained management. We would call it 2FP later. The full name is two-fold parallelism, but it's not important. Our strategy would assign each item to a dedicated location. That's what I mentioned before. So we have to maintain an additional indexing table to do so. To compare, there are really well-developed algorithms for hashing, high-performance hashing, like Google's Swiss table, like Cuckoo, like something like that. They can handle cases like collision and expression very well. But if we want to maintain our own tables, we have to deal with some situations such like read-write contentions on the same table. So we have to use something like logs, some more synchronization mechanism. So that would be tricky to handle. So these differences would make the data management complicated and non-trivial, as I mentioned. So we need to improve the throughput of the whole data management or lookup process to match the training performance of the dense part on the GPU. So let's see our first technique, DIT, or decentralized indexing tables. It could be used to manage the embedding vectors to move the data efficiently. The DIT can be split into 2 parts. The first, we call it indexing. It's used to convert IDs to memory address. Sorry. The DITs are replicated on all the GPUs, so any worker can do it independently. First, the IDs are hashed and point to one DIT. In this example, the ID 1 is pointed to the DIT 1. So this step is simple hashing. Then second, we query the DIT actually to get the location information of this item. By querying these DITs, we can see the ID 01 has a location on device 2 and has its chunk number, has its offset within a chunk. So yeah, this is indexing process. And because this process does not involve any real embedding data, so this process can be performed before the training iteration, as long as you got the IDs. So this is why we call it prefetch. Okay, then the second process is called lookup. So this is where the really data movement happens to copy the data from the embedding chunk to the GPUs. And due to consistency considerations, we do not want to use outdated data because we want to keep the mathematical equivalence to the original training process. So we must not call it too early. So we just call the lookup process before each training iteration, just like the original data loader does. Okay, so DIT is used for accelerating the performance of moved data. Then we implement a local pipeline on DITs to accelerate the query of the DIT. So each DIT on worker is actually further partitioned into different shards. In this example, on a worker, a DIT is split into 3 shards. Okay, a worker can simultaneously serve the queries of different workers from different workers with different threads. So the handling threads will go through the DIT shards in a pipeline fashion. So in the first time step, the thread 0 goes through the DIT 0, and in the second time step, it goes further to shard 1, and another request is now working on the shard 0. So in this fashion, we can eliminate the read-write locks on the DITs because each shard is accessed and locked exactly once by each thread, or we say each query. So there's no contention, so no excessive locking should be used. This indexing pipeline works asynchronously with the lookup operation because, as I mentioned before, the indexing could happen well before the training iteration starts, and the lookup could only be called before each iteration. And consistency is still guaranteed by this mechanism. Okay, then this is how DITs handle queries. But we know both indexing and lookup process still follow the all-to-all pattern because each process or each worker will need to handle the requests from all different workers, including itself. So it would still have contention on some local resources like the embedding data and the DIT itself. So we need to handle this carefully. To solve this, we adopt a ring-like schedule to avoid conflicts in these scenarios. So in each step, each worker only serves one request following a ring pattern, which means from the example, you can see in the first time step, each worker processes requests from itself and simultaneously issue and receive requests from its neighbor. And when the processing ends and it processed the requests previously received from its neighbor and received from another neighbor, and then on and on. So this is an example for we have 3 different shards and 3 workers. If we have more shards and more workers, this situation is similar. It's just a ring-like pattern like in all collective algorithms. So with this schedule, which both applies for both indexing and lookup, we can avoid the conflicts on local resources, and also we have automatic overlap of communication and computation because you can see the receive or the send operation can be done simultaneously with the processing. Okay, so with the efficient data management module, we are now finally able to design a more fine-grained parallel strategy, which we call 2FP. Let's recall the original hybrid parallel strategy on CPUs and GPUs. So typically, it stores huge embedding tables on CPUs and use GPUs for neural network computation. So here, we introduce a special embedding chunk, or we call the R chunk, on each GPU. As its name shows, it is replicated. So we can use data parallel on these R trunks and to not use auto on these R trunks. So we hope that R trunk can cover most embedding access and reduce auto overhead. So how to select the optimal numbers of elements in R trunk is an important problem because the size of R trunk decides the communication volume. It is obviously positively correlated to the all reduced volume because the larger the R trunk, the more all reduced you need to do and the less auto you need to do. So our target is to minimize the overall communication, which adds then to add both ARP. So we have designed a performance module to estimate the communication performance when R size changes. So it has some efficiency. The R is the size of R trunk, the N is the total items of the dataset, and 1 minus rho R is the portion of these items that are not in the R trunk. And CAR and CA2A are just two pre-measured coefficients showing the performance of all reduced and auto operations. So by our observation and experiments in practice, we can estimate the performance quite well with our module. You can see on the right, the red line is our estimation, and the shadowed area below the red line are the actual performance. And the dashed line is our estimation. The solid line is the actual optimal value, and they are quite close. So in our practice, the optimal R size would be between 16K to 64K on typical devices. And because each item in the R trunk takes only about maybe 4 kilobytes or something like that, so we consume only tens of megabytes of GPU memory, so this is a really low storage overhead. But we can reduce auto volume a lot. So let's come to the evaluation part. First, we conduct a metro benchmark of the DITs. We have two things to compare. The first is a baseline that uses naive locking. It means each worker just select its trunk and use locking to prevent other workers from accessing that. It is a baseline. And there is another ideal upper bound. So we use simple hashing in each workers, and it does not read or write, just using hashing to do some data movement. So this is ideal upper ground because there is no contention. Okay, so we can see from this orange line that our pipeline mechanism can bring about 8 times of throughput improvement compared to the naive locking method at this point, the 32 thread point. And to our surprise, actually, with our conflict avoiding schedule, we can even benefit when we oversubscribe, which means we use more CPU, which means we use more threads than the hardware CPU threads. Because of the schedule, you can see from the plot that the blue line still goes up when we exceed the physical CPU number 32, and it stops at 48, and we can get about 40% of performance improvement on our hardware. Okay, then finally, the end-to-end throughput improvement. We conduct the whole training process of 3 different DLRM modules on 3 different data sets on 32 GPUs, 32 high-end GPUs actually. So, and we have 3 state-of-the-art baselines, that is TFDE, that is TensorFlow recommenders, if I remember correctly, and TorchRec. And HugeCTR is a native implementation. It's written in C++. Okay, finally, our system. So we can see from the these graphs that we can achieve about 2 times to 16 times end-to-end training throughput improvement on different scenarios. And we have more experiments in our paper, including the scalability, the weak scaling, the strong scaling, some application studies, and some overhead analysis. If you are interested, please refer to our paper, and we have many more graphs on that. Okay, finally, let's conclude it in another way. I don't want to repeat the performance numbers because they are not important, but we can use a roofline model to show what we have done. While the dense part of the DLRM has high arithmetic density, because it typically consists of like highly optimized jam operations, the communication overhead brought by the original hybrid parallelism, because we need to reorganize data, the communication overhead is very high, so it drags the point down to this part. So if we use our fine-grained 2FP parallelism strategy, that is to replicate some items, some frequently accessed items, it can reduce the communication volume, so it can move the point to the right. But now the bottleneck is the data management overhead. So we further try to resolve this issue by our 3 unique techniques, that is the decentralized indexing table, DIT, the local pipeline to handle queries, and the ring schedule to avoid conflict. So finally, by combining both the 2FP and the fine-grained data management, HypeReca could now move higher to the roofline model to touch the roof. Yeah, and this is what we have done in our work. And thank you for listening. And if you have any questions, please feel free to ask me. And you can also write to the first author in this mail. And HypeReca is now open sourced on our GitHub, and you can download it and try it. Thank you.